These are chapter 5, the beginning of the quick test questions. Which of these best describes why some materials are permanent magnets? These materials contain charges? No, all materials contain charges, so that doesn't explain. I contain charges, I'm not magnetic. The magnetic domains are all aligned in the same direction? Maybe. These materials are made of metal? No, some metals are not magnetic. Like copper, you put a magnet next to copper, nothing happens. These materials are found in the center of the Earth. There's lots of junk in the center of the Earth. Not all of them are magnetic. Some of them are, but not all of them. Now, the reason it is because in a permanent magnet, you have tiny microscopic domains where the electrons, the spinning electrons, are all pointed in the same direction so that they give you a net magnetic field that's all in the same direction. Those are called magnetic domains, those tiny regions, microscopic, where the electrons are all aligned in the same direction, and those magnetic domains are all lined up. So two things. First, they have magnetic domains, but you know what? I got magnetic domains too. It's just my magnetic domains in my body are all jumbled up. And so my net magnetic field is 0. That's true for you too. Sorry to burst your bubble. But you have no magnetic field. Which of these explains why a permanent magnet is magnetized? It has a current through it. That might be true for an electromagnet, but I'm not asking about an electromagnet. I'm asking about a permanent magnet. The magnetic domains are aligned. Yeah, we know this now. Electrons produce their own magnetic field. True statement. That is a true statement, but not why a permanent magnet is magnetized. And ferromagnetic materials are always magnetic. Is that true? Ferromagnetic materials are really just iron, things that are, that's what ferrous means, that they're made out of iron, and iron can be magnetic if it's either made into an electromagnet or if it's made into a permanent magnet, but it is not why ferromagnetic materials are not necessarily magnetic. Which pole of a magnet points towards the magnetic north pole? So if you imagine the Earth, here's the North Pole, and here's the South Pole. The North Pole where Santa Claus lives, though, newsflash, no Santa Claus. Santa Claus is not real. Okay? Sorry to burst. Okay. Crushing all sorts of dreams here today. And then the South Pole, like where the penguins live at the South Pole, but these are called that because if I take a magnet and on the Earth, the North Pole points towards that, and the South Pole, my magnet, points towards that. That means that if I imagine that the Earth is a magnet, that really this is the southern magnetic pole, and that is the northern magnetic pole. So the pole of a magnet points towards the magnetic. Which pole of a magnet points towards the magnetic North Pole? Well, the magnetic North Pole is here, and so that's going to be the south pole of the magnet on your compass. A negative charge enters a magnetic field as shown. In what direction will it feel a force? I just did a video that had some extra practice for right-hand rule, but here, refer you to that. But here, V, let our index finger go in the direction of V. Our magnetic field, that's going to be our middle finger. So you use your middle finger for something more useful than what you usually use it for. Let that go, the magnetic field. Index is your V. My middle finger points out of the page. That means that my thumb is going to be pointing to the right with that orientation. Index, thumb, and the middle finger will come out of the page. But because this is a negative charge, the answer is not going to be to the right. Instead, I'm going to take the opposite, only because it is a negative charge, and the answer is going to be to the left. what is the initial direction of this positively charged particle when it enters the magnetic field as shown? So, index finger in the direction of V. B is down. That's going to be my middle finger. And then my thumb is going to be into the page. So C is into the page. It is a positively charged particle. At some moment, an electron moves with a velocity of 1 meter per second in a 1 Tesla field. The force acting on the electron is what? Well, F is equal to QVB sine theta. I don't give you the angle here. Oh wait, no, I do. So the velocity is 1 meter per second, and it's very important that you see this in the same direction as, that means that V and B are in the same direction. Now, that means that the angle theta is 0 degrees. So the sine of 0, as you know, is equal to 0. And so the force acting on this electron is equal to 0. That was all, yeah.